So I'd like to now introduce Adrian to everybody. He did his undergraduate degree at the Universidad Politécnica de Madrid, and he did his PhD there in the Turbulence group with Javier Jimenez. And then he joined the Center for Turbulence Research, led by Parviz Moin in Stanford University, where he's been there since 2016, I believe. He's also frequently one of the hosts at the summer turbulence schools that are held every 2 years in Madrid. The fourth one was last year. And he'll be starting a faculty position at MIT in January 2021. So thanks again for giving a seminar for us.
So thank you for the introduction, and also thanks for the invitation and for this opportunity to share my work with you, and also thank you for joining this talk. I'm gonna talk today about cause and effect in wall turbulence, and my goal here is to show some motivation of why I think this is useful, and show a few applications, and also some cases that in some cases where this can be used to not only for applied cases but also for development of new theory of understanding of the flow. So before diving into that, of course, I want to first acknowledge my collaborators, so different people that they have helped me to do these pieces of this work. So I'm really very grateful for that. And also the funding from CTR, that is an ONR. Also, I would like to thank the ERC, because part of this work has been done thanks to the summer program organized by Javier Jimenez. So I also would like to thank him for all this opportunity and the resources to carry on this work. And now I want to also remark a little, or talk a little about this like a global vision of this turbulent research. And this is what I'm showing here in this plot. Like the title is More Than a Century of Turbulent Research. And I just went to the Web of Science and took how many papers are published related to turbulence. So essentially I look at when the title or the abstract or the keywords, somehow they mention turbulence. And you can see that there is this steady trend that the number of publications keep growing and growing. In time, we are now close to 10,000. And it's curious this because you can really look at other fields, for example, that you would consider emerging disciplines. I just decided to take here one of them. This is one example, for example, nanotubes. And you can see that in this case, the field was non-existent before, and then suddenly it jumped, it grew up very, very fast, much faster than turbulent research. There was a point in which there were more publications on nanotubes. But then the field saturated, and then you see that even went down a little, and now turbulent research again catch up with this. And I hope that this is gonna keep growing steadily. And one of the reasons for this that I think is important to remark, especially in a conference like this about fluid mechanics, is this like overarching structure of turbulent flows. This is what brings me to this slide, where from really large scale systems like stars, like aerodynamics, or environmental science like atmospheric boundary layer, are also biofluids. Somehow turbulence is present across all these systems. And I think that that's exactly why we see this trend in turbulent research, in which everything is very robust and it keeps increasing and increasing because it's somehow connected to all these other disciplines. There are also some important facts. This I got from one of the reviews of Jimenez, in which we are aware that indeed, because of these turbulent motions, there is a strong impact in terms of the energy when we move the fluid, just a vehicle or pipes or canals. And we know that it has to do with boundary layers close to the wall. There are also some impacts because of the CO2 that is dumped into the atmosphere because of this. So coming back to this, I think that somehow explains this trend. And this trend keeps growing, not only because there is this overarching theme of turbulence, but because we still have some challenges ahead. That is the way I would like to also frame this talk, to think about what are those challenges. Here I'm just giving a very superficial view of what I personally consider those challenges are, or at least some of those. Some of them are related to physics. So we have somehow some conceptual models and theories of turbulence. Most of them somehow they emphasize a lot the kinematic, kind of a static view or kinematic view of turbulence. And somehow I think that we are missing to include some dynamics. And this is where this cause and effect is going to come into play. And there are also challenges in modeling that many CFD predictions that we have, indeed, they are still far from this stringent tolerance that is demanded by the industry. Usually they would like to have like less than 1% error in these predictions. So in having this as like a global view of what are the challenges, I'm going to talk here about this cause and effect as kind of a new way of looking at this to try to tackle at least part of these challenges that we have ahead. So for that, the talk is organized in these 4 blocks. The first point that is kind of is going to be the main topic of all the talk. It has to do with how we can define a framework based on cause and effect for fluid mechanics. There are different ways of doing that. The way I'm going to focus on in this talk has to do with information theory. And then once that I establish and kind of motivate why this may be useful, I'm going to show you three examples of trying to solve 3 problems with this, because at the end, what we are interested in is not so much in the method itself, but if this is going to help us to solve the problems we are interested in. And for that, I'm going to show 2 applications. One has to do with, it's very applied with some aircraft, the performance of the aerodynamics of an aircraft, and the other has to do with some theory of the energy containing eddies. And the last application is also connected to the theory. It has to use that information for some forecasting. So then let's move to this first point, and which I'll try to motivate why we should think also in terms of this framework. And for that, I usually like to use this picture. This has nothing to do with fluid mechanics, but sometimes I use it because I think it's very intuitive to convey the message. So this is just a snapshot of a basketball match. And imagine that we don't know anything about basketball. And then I ask the following question to myself is, can I understand basketball just by looking at this frozen snapshot? So this would be the question. And if you think about it, because we know somehow how basketball works, you can already tell that this is going to be very challenging. It's true that if you just look at these frozen snapshots of basketball, you can probably understand many things about the game, but you are going to be missing the dynamics. And somehow we know that there are some cause and effect, like how the players move, what they do. And we don't want to understand only some basic statistics. What we would like to know is the rules of the game, but even more, we want to understand the tactics and the strategies that they are followed. So that will be our final goal. So it's obvious that we are not going to be able to do that just looking at this frozen snapshot, even if we have many of them. So we can indeed take this and rephrase it for a turbulent flow. Because at the end, if you think about it, I can ask, can I understand what is happening in a turbulent flow just looking at a frozen snapshot? So it's kind of the similar answer. It's true that I can probably understand many things because this particular configuration is a consequence of the time evolution of the turbulent flow. But still, we are going to be missing many things. And the question is if we can really find a way that, or some approaches that they are going to help us to understand what is happening in time. And there are many tools, I'm kind of giving some overview or summary here, tools to understand turbulence flow. And these are common tools that I have used myself, and they are still very useful. And I plan to use them, so that's perfectly fine. But I think that maybe one limitation of all these tools, although some of them, they give some information in time, they are not designed specifically to assess what is the cause and effect in a turbulent flow. And this is what the point that I really want to emphasize is, can we really frame the problem in a way that cause and effect is central, is really the central insight that we want to understand in the flow. And for that, it comes to the question of, well, how I'm going to measure this cause and effect or this causality. So then I'm going to now try to introduce and motivate the method I'm going to use. For that, because we know that causality has to do with time, So the key here, the key quantities that we have to look at are somehow time signals. And for this example, I'm using 3 time signals. Are these signals here that I'm calling U, V, and W. You can think of these as velocities if you want, but they don't have to be velocities. It could be anything, any quantity that is a function of time. And it doesn't need to be constrained to 3 signals. I could have 20 signals or whatever I want. But just for the purpose of this presenting the method, this is enough. So a way of introducing the concept of causality is just using this intuitive idea that we have, is that I can define the causality from a signal V to another signal U as how much knowing the past of V improves what I know about the present of U. And if you think about this, is again somehow consistent with our intuition. What this is saying is that if I know a lot about this variable, what happened before, that's going to help me to understand what is happening now in other variables. So this kind of concept can be linked to causality. And obviously this is just like an intuitive definition. So I need to formalize this in a mathematical form. And for that, I need a quantity that describes these 2 properties or contains these 2 properties. Here I'm talking about past and present. So somehow whatever quantity I use, it has to be related to the arrow of time. So this is going to be important. And also here I'm talking about knowing something. So there is this concept of knowledge. So somehow whatever quantity I use to measure causality, it has to quantify the knowledge, or a different way of framing the problem, certainty. So it's the lack of knowledge that I have. So if you given this definition, and we know that these 2 properties, then the correct quantity, one of the candidates as a correct quantity to define a causality has to do with the Shannon entropy. So this quantity comes from information theory. It's something that is well established. Essentially, we have a signal U. This entropy is defined as the expectation of the log of that probability of that a given event happening. So this is something that has been studied a lot, and it complies with those properties. But rather than trying to emphasize those mathematical properties, I will try to convey for this talk just the intuitive idea of why this is the correct quantity to then build a causality. And for that, I like to use this example. I think that this example can somehow illustrate how entropy can be a marker of the direction of time, and also it can be a marker of uncertainty. And consider this example that indeed it has to do with fluid mechanics. Imagine a case in which you have milk and coffee, and they are separated completely. So now you know that this system, if we integrate this system in time, what is going to happen is that they are going to mix. So they are going to mix in time. And what happens is that when they are mixing, so this entropy at a given point in the flow is increasing. So we can already see that this concept, I mean, we have a quantity that is clearly changing in time when the system is evolving. And then before, you can also see that this is related somehow to uncertainty, because before it was very clear where was the milk and where was the coffee. And right now it's not so clear. Like even a position in a space, there is a probability of finding milk and a probability of finding coffee. So that somehow is also related to the uncertainty. So that links to the second concept. And now let's imagine this case. Imagine that the system is in this state. We have milk and coffee mixed. And then as a function of time, what is going to happen is the opposite. They unmixed. And then you get completely well separated milk and coffee. So in this case, you could really tell, looking at the entropy, that the system is very, very different, the way it behaves. The entropy is completely changing. However, if we look at other quantities, for example, the mass, the conservation of mass, the momentum, the energy, both systems, they conserve a mass, they conserve momentum, and they conserve energy. So it's true that those quantities, they have somehow causality in there, but they are not the key to understand the direction of time. And however, when we were looking at the entropy, that one wasn't conserved, and that is the one that was telling us in which direction was the system evolving. It was telling us what is past and future. So I think that this somehow, in an intuitive way, justify why we can use entropy as a good candidate to construct this definition into a mathematical formula. So this is the formula indeed, the way we can do it. This has been done also as a part of information theory by Schreiber in 2000. And in particular, this is usually referred to as a transfer entropy. Although here I'm going to use the notation of causality because it's more clear. But technically, the way this is called is information theory is transfer entropy. So essentially, the causality from V to U is defined as this difference of two entropies. And now there is a bar here. The bar means conditional entropy. That is very simple to define because entropy is based on probabilities. So we can compute conditional probabilities. So that's the way this bar works here. And then I'm defining these signals here that are the lag in time. So I'm using the minus to denote that they belong to the past. And then these two terms, what they mean is the first term is the uncertainty of this variable U, given that I know the past of V and W, but I don't know the past of V. And then this is the conditional entropy, assuming that I know everything. And if you think about it, this difference is exactly what is giving me the extra information that is coming from the variable V. And this is the way of formalizing this. So probably for people that are not familiar with the information theory and with this definition, this could take some time to process and to really grasp completely, but that's totally fine because what I think that what is important here is that this was the key concept. The way I'm defining causality is somehow based on the knowledge that I have of the signals in the past and the present, and is based on transitional probabilities at the end. So that's, I think, that the key idea here of how to use this. So this would be the end of the method. So now, of course, this is just a method. We are not solving any problem here. What we want to do with this is to see if this is going to be useful for our particular interest. And I'm going to start with this case that is probably the most applied of all the cases, that it has to do with improving the aerodynamic performance of an aircraft, and then this information theory approach is going to come at a given point to achieve what I want. So let's motivate the problem here. And I think that for each individual problem, I'm always going to try to motivate this because, again, I like to insist on that at the end, I'm not so concerned about the tool. I'm more concerned about the problems that I want to solve and if this tool is going to help me to do that. So usually when you have an aircraft and it's landing, we know that there is a lift. That's what is keeping the aircraft on the air. And we know that this force, the lift, is proportional to some coefficient, I'm calling here CL, and then the velocity squared. So what we really want to have is when the aircraft is landing, we want to have a lift coefficient that is very high. And there are different reasons for that. Like you want to have a lower landing velocity, the runaway is going to be shorter, you are going to have safer operations, you are going to have less environmental impact. So that's what ideally we would like to have, and that's why you know when the aircraft is landing, you see that the slats and the flaps, they are opening, and that's exactly what we are trying to do to increase the lift. So there are different approaches that are somehow exploratory for increasing the lift, and an approach is based on adding an active flow control, is adding a jet. So it's adding a line across the wing where we are going to inject some air, and that is going to help us to improve the lift of the aircraft. Here I'm using just this sketch to, in an undefined place, setting up these flow jets. There are very particular configurations that people are exploring. This will be one case. This has been proposed recently by NASA. They are indeed running actual experiments on this wing. So what they have done in the wing, they remove the fairings that they have for opening the flap and slats. There are no flaps and slats anymore, and they are saving weight because of that. And they use that extra weight to include the system to have these flow jets here. And that is the question is, okay, so is this going to help us to improve the lift of the aircraft? And indeed, they are going to release the results for these experiments soon. They are not available yet, but that's going to be very interesting to look at. So I'm going to use, instead of those experiments that are not yet available, I'm going to use other experiments that are already out there. This is called the JAXA Standard Model High Lift Experiment. You can see here how it looks like. It's essentially an aircraft in landing configuration, and you can see that they have different probes here to compute and to measure the pressure. So this is a 21 degrees angle of attack. It's very low Mach number because it's landing configuration, and Reynolds number is of the order of 2 million. So this is another result that they get from the experiment. This is like fluorescent oil film visualization. Essentially, they paint the model with some oil that is fluorescent, and then they run the wind tunnel, and after some time, they can really see the footprint of the turbulent flow on top of the structure of the aircraft. So what I'm going to do, I'm going to use the data from this experiment as a reference to make sure that I'm computing things well in the standard configuration. I'm going to have a simulation of this. So this is going to be now my simulation. And for that, I'm going to have a large eddy simulation of this full aircraft. Here I'm detailing some of the parameters that I'm using for modeling. So this is a LES. I have a Brema model, and this is high Reynolds number, so I also need to use a wall model. Unfortunately, I don't have a lot of time to describe how are all the intricates of this simulation. I want to mention that it's not something that is trivial to do, so this already requires some work to generate the grid, to use the proper models, and to the wall models, and make sure that everything worked fine. But for you to have an idea, I'm using of the order of 180 million control volumes here, and this takes like 2 days using 1,000 CPUs and using a solver that is developed jointly by Stanford and Cascade Technologies. And what you see here in this plot is the friction at the wall, so it's the footprint. So you can somehow see what are the smallest scales that I'm able to resolve. In this case, that are still much larger than the viscous scale of this problem. But still, this seems to be working fine. This is the result we wanted to look at. What I'm showing here is the lift as a function of the angle of attack. When you see the solid line is the experiment, and this blue dot is the simulation. So we are doing a good job right now of computing what is the lift of this case. So this is going to be my starting point, indeed. Now what I'm going to do is more difficult than this. The question that I want to answer is, well, can I increase the lift coefficient using the active flow control that I introduced before? And in particular, one decision that I have to make is like, where do I have to place that control? What is the best location for that? And that is when I'm going to use the causal analysis for that. So let's go to the setup of the problem. I'm going to have, again, the aircraft that is similar to the same simulations that I have before, but now I'm going to have a jet here. So this is what I want to know the properties of this flow jet. This flow jet is defined by some maximum velocity and also a frequency. So this is what is called a zero net mass flow. So essentially, we are not injecting any extra mass through these jets. And in just some basic dimensional analysis for this lift coefficient, what we will get is that this is going to depend on these 5 parameters. Essentially, the Reynolds number, the angle of attack, the momentum coefficient, that is just a ratio of how much is the momentum injected by the jet compared to the full momentum of the aircraft, and then the frequency of this jet. And then also, for the sake of simplicity for this talk, what I'm going to do is to fix most of these parameters. Many of them are already given, like the Reynolds number is given, the angle of attack is given. Even this momentum coefficient is somehow given by what we can do, like the weight, the extra weight that we can impose in the wind. Usually the values are like 0.015. So I'm going to take that. So the frequency, indeed, I could choose not to use this particular one. And indeed, this frequency can be computed as a part of this process. So I can use all this methodology that I'll use later to estimate what is the best frequency. But I decided for now just to fix it here. So you will have to take my word on that. But this could be also part of the analysis. Yes, I'm fixing that to simplify things. And then the parameter that I have free is the location of the actuation, like this X location for the actuation. So the question here is, do I need to actuate closer to the trailing edge of the wind, or do I have to actuate closer to the leading edge? I mean, what is the best way of doing that? And there are many different ways of solving this problem, this control problem, and the way I'm going to approach that is using the information theory. Before that, still mean, the tools are not going to solve the problem for us. We need to understand what is happening and why we have this problem and what we have to do. And for that, somehow we need to inspect and look at the flow and how is the flow structure. So this is just a side view of the aircraft. I'm going to zoom in into the wing. And what I'm showing here right now is some snapshots of how is the flow evolving in time. So this is the result of my flow without any control. This is what I'm calling the baseline case. This is the one that I have shown before. So I'm going to compute this average flow field. This is how the mean velocity looks when you select a given plane that is crossing the core of the wing, and the color is the velocity, and I'm also plotting here some streamlines. And this is already showing what is the problem. So the problem is this vortex that we have at the trailing edge. Essentially, we are spending extra energy in making the flow rotate here, this recirculation, instead of using that extra energy to increase the lift. So somehow this is our problem, and we want to get rid of that. So what I'm gonna do is to first focus on this region of the flow that I'm gonna fix. So that's really my target. I want to know the causality between the rest of the flow and this region. So this is gonna be one of my signals that I'm gonna define. The second thing that I'm gonna do is to select another region of the flow. So I'm gonna have two windows. For example, this one here close to the leading edge, and then my vortex. And then the next step, what I'm gonna do is to compute the instantaneous kinetic energy in each window, and I'm gonna use a POD decomposition. And if you're familiar with POD, then probably this is very straightforward for you. If you are not, you can think of this like a generalized Fourier transform. Essentially, what I want to do is to separate my velocity field in two components, one that depends on space and the other one that depends on time. Because I mentioned before, causality has to do with time. So somehow I need to extract what is the time evolution of the quantity I think is important. So I'm setting here that I think that the kinetic energy is important, and I'm going to decompose this kinetic energy into these two components. And the third step that I'm going to do is to compute the causality. So I want to know how much influence has the flow here to this region here. And that's going to give me a number. And then I'm going to repeat this. I'm going to repeat this. I'm going to have a sweep of different windows getting closer and closer to the trailing edge and closer. So essentially that's going to give me for each position how much is the causality from that region of the flow to this trailing edge vortex. And then the plot that I want to look at is this one, indeed. So this is the one that has the key of what I have to do. So in the vertical axis, I have causality. This is a normalized causality. I didn't emphasize that before, but causality has to do with information, and it has units of bits. But I don't care so much about how many bits are transferred from one region of the flow to another. I'm more interested on this, just the relative influence. So that's why this, well, the maximum here is 1. And then this X is just the core of the wing. So I'm moving across this core. And well, this is already telling me what I have to do. There is some increase of causality after you get this 0.4, and then it goes down, and then it seems to saturate somehow. So what this is telling me is like I have to actuate here. So this, whatever I do here, has a very strong influence in this vortex there. So now that I know where I have to actuate, I'm gonna go back to my problem, and I'm gonna set up a new simulation. So it's essentially the same setup as I had before. It's an LES with the same modeling parameters. The main difference now is like I really have now this jet here actuating across this region that I have found out that should be the most influential into this trailing edge vortex. And so I repeat the calculation, and we can look at the results. So this was, I'm going back to this plot, this was the baseline case. And then I can introduce the control, and then you see that this vortex disappears. So in principle, our intuition was correct of what should happen. We wanted to get rid of that, and then this has completely disappeared. So let's look at exactly how much we increase the CL, if that is also working. And it seems to be working just intuitively by looking at the previous like average flow field. We knew that it was somehow working. So now I have again this angle of attack that I'm choosing the control. I'm calling here the simulation, and then the control simulation. So you see that there is some increase here of the lift coefficient as we were expecting. So there are a few underlying assumptions here. For example, we were assuming somehow that when we are going to control the flow and modify it, this was going to still going to work. And it did work in this case. It might be that in other cases it doesn't work. But I also want to emphasize that in this case, I only needed one simulation before, just the base flow, and that was enough for me to know where I have to actuate, or at least to have a very good guess of where I have to actuate. So that's a huge saving compared to other methods that they try to use a joint, for example, and they are computationally very expensive. In this case, I already have some data from a base case, and that was enough to make this estimation. There is something else that we can do just as a sanity check. That is, why don't we use a correlation? And well, I'm using this also to show how this prediction by using a correlation is going to change a lot. And so essentially, I'm taking the kinetic energy again and these coefficients, and what I do is to correlate. What is the correlation of the kinetic energy between one point and this trailing edge vortex? And I'm also plotting this here. So you see what is happening is, like, as you get closer and closer, correlation goes up, especially it goes very fast up at the very end when you get very close to the vortex. And this is somehow expected because correlation has to do with intensities. So that it is not related to sensitivity to, or the impact of changing something in the flow to what is going to happen in another place. It's just purely correlation of intensity. So the intensity is high here, it's also high there. And well, I get a prediction here. My prediction is that I have to actuate very late. Let's do that just to show what happens. So I'm going to introduce my actuator. Now it's here. And now you can see what happens. There was some change indeed. This is not the base flow, this is the actuated case. So there is some change there, but we don't get rid of this recirculation completely. And we can look at the CL, there is some impact. Indeed, we are able to increase the CL by a little, but still this impact is much smaller than the one that we had before. And again, I think that this highlights in a very clear example, this difference between correlation and causation. Essentially what is happening here is that it's too late to actuate. By the time, what we want to do in this case is to inject momentum such that the boundary layer is attached all the time. It's also attached here. And by the time we do this here, it's too late. We cannot inject enough momentum to really get rid of this vortex. However, if we do it there, as I was doing before, then that's enough. I mean, and that was predicted by this cause and effect, that it wasn't based on intensities, it was based on transitional probabilities, but it cannot be captured by a simple correlation. So I think that this example kind of shows how we can use this new way of thinking of cause and effect to use some real applications for aerodynamics. And I hope that example was exciting enough. And the one that I want to discuss now is something very, very different that I'll spend maybe the rest 20 minutes to talk about this and the application that has to do with theory. So I've shown before how this can be used in a very applied case. So the question is, okay, can we also use this to understand what is happening in a more fundamental way in the flow? And for that, I'm going to talk about this similar causality of these energy containing eddies. This part that I'm going to present is published in GFM. If you want to look at the details, probably I'm going to need to skip a lot of them, but they are all there in the paper. And also there is a summary video on YouTube. It's only 5 minutes. So maybe you can also take a look at that if you miss something of this talk. So now my setup is going to be just a flat plate. I'm going to have a boundary layer, and this delta is going to be the thickness of my boundary layer. And this U just represent the inflow, and the wall is going to be here. So we know that we have this chaotic motion of the fluid. This is obviously just a sketch. I can get some actual velocity field from a simulation. This is a turbulent channel flow. And what I'm plotting here is the span waist velocity. And I'm bringing this because what I want to highlight is the way we envision how this flow is organized. So essentially, maybe I've been looking at this plot for a very long time, but to me it's very clear that even if this looks very complicated, it's not random. So there is some organization here. And in particular, you see that sometimes you get this like yellow that is positive span-width velocity regions. And then sometimes you get these blue negative span-width velocity regions, and they seem to be all around the place and different sizes. And indeed, you can show that when you look at these regions, those are the ones that contain most of the momentum and the energy of the flow. And what happens usually is that they start close to the wall and they extend up to a given height, and some of them are large like this, and others are just small, like the one that I'm highlighting here. And as I mentioned before, we have many of them all over the place. And we can think of a boundary layer as this, as a collection of these wall-attached energy-containing eddies. This first original idea was proposed by Townsend. Is the attached eddy model, in which we envision the boundary layer as a collection of multi-scale population of attached eddies. There are many reviews by this. For example, one by Marusik is a very good review to have an overview of the different works about the attached eddy model. And these eddies, indeed, they can be very different in size. If we think of a boundary layer, these large scales could be maybe 100 meters, and we can find scales that are smaller, still not at the viscous scale, but just smaller than the ones of the 100 meters, that they could be centimeters. So you can really see how different these could be in a high Reynolds number setup. And then the question I want to answer here is the next one. So I want to know if these small, I'm going to call these smallest energy eddies, that usually they have sizes that are of the order of the boundary layer thickness divided by the Reynolds number, if whatever dynamics they follow are similar to the dynamics of these, what I'm going to call medium-sized energy eddies, those that are a fraction of the boundary layer thickness. So I want to know if essentially one is just a re-scale version of the other in terms of scales, time scales, length scales, velocity scales. So this is the question I want to ask. And to do that, I'm going to use obviously the framework of information theory as a way of quantifying the dynamics. And for that, I need 3 steps. I need to define a simulation. I want to simulate these small eddies and these medium-sized eddies. And then again, to quantify causality, I need time signals. So I need to quantify energy eddies as time signals. So that's going to be the point 2. And once that I have that, then everything is straightforward. I just need to quantify what is the cause and effect of these energy signals that I got. So let's move to the point 1. As I mentioned before, I'm going to have 2 simulations. So the goal of these 2 simulations is to isolate the energy eddies of 2 different sizes. One is a simulation for the buffer layer, and the other one is a simulation for the medium-sized eddies, that is essentially the log layer. So these boxes, they have been studied before. I'm not going to go into detail so much of how do you select these sizes, but you can look at that into many of the Jimenez work. Essentially, when we have this small box, is tailored such that we only fit this small eddy, and the large ones, well, they just don't fit somehow. And in the other hand, when we have these medium-sized eddies, we can fit a given size in the box. And of course, we are going to have eddies that are below all the ones that are the hierarchy, this Townsend attached eddy hierarchy that we are going to have below. So that's going to be there, but what I'm going to do is to filter. I'm going to filter those, so I get rid of the contribution to the energy of those eddies. So that's the way I'm going to define my 2 setups. And essentially, this is a direct numerical simulation. I'm going to solve the Navier-Stokes equations to give you a feeling. This box is around 1 million grid points, and this is around 1 billion grid points, American billion. So let's zoom in into one of these boxes to see what is going on there. This is the simulation for these buffer layer eddies. This is a normal setup. We have a periodic boundary condition, and then we have the wall here. Rho RE tau is 180. What I want to remark of this simulation mostly is that this time resolved, and I have a very long time history that's going to help me to quantify the causality later. Everything else is a very, very standard setup. Also, I'm going to use this notation of U, V, and W. U is the streamwise, and V is the wall normal, and W is the spanwise velocity. So now we can look at the medium-sized energy eddies. These are the log layer, and I'm really putting here at the scale the simulation for the small energy eddies. So you can have a reference of the different size. In this case, Reynolds number is much higher, And I have again run this for very, very long time. And you can see that there is some resemblance in which what I'm plotting here is an isocontour of a stringwise velocity. There seems to be some streaky motion, and sometimes this streak breaks, sometimes it forms again and it meanders. But you can see that in this case, everything looks much more turbulent. So once that I have this, so I have my simulations, you can have a feeling here of how different they are in size. What I'm gonna do is to define these eddies as time signals. So I need to somehow characterize what is the energy doing in these different simulations. I'm gonna use this box for the log layer eddies, the medium size, but it's exactly the same for the small simulation. Essentially, what I'm doing here is to select a given band such that I only capture the eddies that are, in this case, in the log layer, and I don't get any influence of the eddies that are below. I'm going to make some average there, and then I'm going to compute the Fourier transform in the span-wise and the string-wise direction. So this is this U that I'm using here. The notation that I use is U01. So 0 is the string-wise wave number. It means like there are no variations in X. So you have something that is constant in X for a given span-wise location. And then 1 means that you have one variation. So you can see the flow is changing from positive to negative. And this is from here, this is going to have some coefficient associated with it that is changing in time, this mode. And this is what I'm representing here. So this is what is really characterizing what is the energy doing. So it's telling me when the energy is organized in this way. For you to have an example, this is a video of what is this mode doing, the 0-1, the energy in that mode. And below you see an instantaneous flow field. And I just stopped the video here. Essentially, when this peaks, you see what you should expect to see, like the flow is organized in this very elongated structure. And we repeat the same for other wave numbers. For example, the 1-1 is kind of the same story again. This is characterizing when the energy is organized in this motion. And we repeat this for different, the different velocities and different wave numbers. In particular, I'm selecting 6 of them. And this is capturing roughly 60% of the turbulent kinetic energy, just using only these 6 signals. And I have done this for the 2 simulations. So I'm going to have a set of 6 time signals characterizing the energy in this box. And I'm going to have another set of 6 time signals characterizing what the energy is doing in this very large box. And then the next step is to compute the causality. So how are these signals interacting? How are they transferring information one to the other? And this is just a summary of what, so we don't get lost on what I'm trying to do. So I have these simulations. These are the set of the signals. And now let's look at this. Let's compute the causality between all these signals. To that, I'm going to need only one plot. So at the end of this, I'm going to look only at one plot that is going to tell me if the dynamics here and in the small and large box are similar or not. And this is what I'm calling here a causality map. Essentially, the way you read this, I have my 6 time signals here. This is going to be the cause. And I have the same 6 time signals in the vertical axis. This is going to be the effect. And the way you read this, if there is some value here, this is telling me how is the causality from this signal to this one. So this is the causality from the mode U11 to V01. And I mentioned that before in the previous example, this has some units that has to do with bits. I don't want to look at that. I'm going to have some normalization. So I'm going to define this normalized causality. There are different ways of doing it. Essentially, I'm normalizing the signal that is the cause. So that's why it's normal. So at the end, this value is going to be between 0 and 1. And that's going to give me a reference of how important is this causality. So this is it. This is everything we need. Then we can take a look at the plots that we were waiting for that are this. So what you see on your left is this causality map for the smallest energy eddies. And what you see on the right is the causality map for the medium-sized energy eddies. They are not exactly identical, of course, there are some differences, but to me at least what I will conclude for this is that they really look very similar. You can see that when the spots where the causality is strong, it's strong for both systems. And even the values are roughly similar in both cases. And if we think before, like these boxes that I'm bringing back here again, if we think again of the size, so these were really very different size. And it's very remarkable that the maps are so similar. So my conclusion would be like, well, this seems to imply that the mechanisms that are in action in one case and the other are very comparable, at least in terms of the energy eddies. And there is one more thing about this plot that I like. I'm gonna first put them together because they look very similar. And something that I also like of this plot, that I'm gonna go into many details, but I want to highlight that, is like this somehow provides some unified vision of different mechanisms, and they are all in one single plot. So we have different ways of studying the flow. Usually, if we really want to study the flow that is non-linear, what we do is to linearize the flow, and that's why we have some linear theories of turbulence that they explain some mechanism, like the lift up or the Ore effect, or modal instability or meandering of the streak, breakdown, formation of rolls. So if we select the highest causalities that we get here, they are indeed consistent with this mechanism. And if you are interested in more details about this, you can take a look at in the paper. There is some discussion about how these causalities are connected with these linear mechanisms. And I think that somehow, I find some value there, because I didn't have to linearize the system somehow. I mean, it was a non-intrusive approach to look at the system instead for isolating the eddies. But apart from that, the way I was trying to assess the dynamics was a non-intrusive way. And with that, I just have 5 more minutes to discuss one small example that could be understood as a consequence of this. And that is this application. If that I just learned about the theory, if that I can use that to make some useful predictions and have some computational savings. And this is what I want to do. I want to forecast what is happening in these medium-sized eddies, but I mentioned before, this is an expensive simulation. I want to use a model that only uses information from these small-sized eddies. That can be done somehow. There is indeed a theorem that is by Barnett, in which if this causality, as we have defined with transfer entropy, can be formally proved that is related to the relative error in an autoregressive model when these variables are Gaussian. So if the variable, they are close to Gaussians, you can prove this exactly. If not, you cannot, but still there is some proof that, some intuition that this is still gonna work. So the fact that these two simulations of the eddies of different sizes, they have the same causality map, is suggesting that they contain the same dynamics, that they can be used for modeling independently. And again, I'm bringing this here because, as I mentioned before, one simulation is 1 million grid points and the other one is 1 billion. So ideally, I want to have the cheapest one to get a model and then apply it to real cases. And this is the problem that I'm posing to myself. I chose just one component, the vertical velocity. This is like the bursting in the flow. So I have a signal like this, and this signal is extracted from this the medium-sized eddy data. Is this video that you see there. So what I want to do is to predict this. I can use many different models. Even I can use a linear model. It will work the same. But usually when you have a signal that is as a function of time and you want to forecast time and you have a nonlinear system, the way to go is to use a nonlinear autoregressive neural network. That's the one that I have the sketch here. This is, I'm going to call NARC. But as I mentioned before, it's not so important, the structure of this neural network itself. This will work with a linear model the same way. So before I can make any predictions, what I have to do is to see how this works. So I want to have some known values. These values are going to be the values of the signals in the past. And I'm going to make a prediction at the present of this variable. So I'm going to use the 6 signals and I'm going to make a prediction of now what is happening now. And before that, I need to do some training. And as I mentioned before, I want to train this neural network not using the medium-sized eddies that are the ones that I will predict. I want to use this small box that I have here, and all this network is gonna only see the dynamics of this box. It's never gonna see the dynamics of the large eddies. And I train that, and that takes some time, but as I mentioned, the simulation is very cheap, so I can really generate a lot of samples of that. And again, the rationale here is like, well, if they have the same dynamics as I have seen before, it means that somehow they contain the same dynamical information, so it should work. And I'm showing here the results. This is what happens. I'm adding now here this dash line, and somehow, as you can see, is doing a pretty good job. I'm not showing that here, but you can do the same thing. Instead of using the small box, you can use this medium-sized box, and there is an improvement that is of the order of 1 or 2% improvements, but still this using just the information from these small eddies was enough to predict what the large eddies are doing. And I think that this shows in this plot very nicely that that's happening. And with that, indeed, that's it. That's the last point that I wanted to discuss. For my conclusions, I'm bringing back this, the outline, indeed. This was the outline of my talk. And just to highlight what I have tried to show here, the message that I was trying to convey, I'll try to convey the message that the turbulence is a very active field still, and there are many exciting things to look at. And one of them, it could be related somehow how things are changing in time, and in particular, how to frame a problem in terms of cause and effect. And I try to emphasize that at the beginning of the talk, and then I hope that with these 3 examples in which somehow there is cause and effect framework coming into to solve a problem in a different way of what you would do traditionally, can illustrate that this has a lot of potential for the future. And with that, thanks a lot for your attention, and I hope that you enjoy.
Thank you, Adrian.
Thank you very much for that great talk. We would like to invite people to ask questions, so please either raise your hand or, I see we have one question already. Go ahead and unmute yourself, John.
Hey, Adrian, can you hear me?
Yes.
Hello? Yes, fantastic. That was a very nice talk. It's an interesting way to think about turbulence. I have a question. In all of your cases, you have taken the time history of one variable to predict a different variable using this causality framework. Is there anything theoretically stopping us from using the time history of one variable to predict that same variable's future? Or, because I noticed you didn't do that at any point.
That's true. In the case where I was showing the theory, I didn't talk about self-induced causality, and indeed it's defined exactly the same way. So you could indeed use that, and you will get some results. There is a reason why I excluded that, is because I was interested in looking at how different variables are interacting by themselves, and that's why I decided to omit that. But the definition and everything works exactly the same. So there is absolutely no problem with that.
Okay, but related to that, I saw in your causality maps that you did actually, along the diagonal of those causality maps, you have that sort of one variable related to itself. But the values were always 0, I think, implying there's no causality there. So what explains that?
Yeah, thanks for this, because I sometimes forget to remark this. That's true. I have a value here. I'm not showing that value. It's the self-induced causality, and it's usually very strong. But I'm not showing that because that's not, I mean, it's kind of obvious. Like, you can use the information of yourself to understand a lot about yourself. So that usually happens because the variable itself contains a lot of information about itself. So in that case, if I plot those values, they're going to be masking the rest somehow. But they are there, and the approach to compute them is exactly the same. In this case, as I mentioned, I wanted to see this relationship between different variables.
Okay, thanks.
Looks like we have a question from Daniel. Please go ahead and unmute yourself.
Yeah, hi. Hi, great talk, Adrian. I had a question about the first section. Are you setting the angle of the jet to be parallel with the free stream of the flow?
Yeah.
Yep.
I didn't make, no, I'm not. So there is an angle there that is like 15 degrees.
Okay, so why have you set it to that?
So there is a reason for that I didn't go into, just not to make things more complicated, just for the people if they don't know. So this jet that I have here, you don't see, but out of the plane there is a small angle out of this, and that I also is also a parameter that could be an outcome of what you get.
That's
And I just follow the literature, like
okay.
some previous knowledge that was there, because at the end my point wasn't so much to try to find the best control, but to see if this may work for those cases.
Okay, so I think that answers my other. I was going to ask if you've looked at actuation along the whole span of the wing or multiple lines of actuation, but I'm guessing that's a no if you were just following literature.
Yeah, I think that I haven't done that.
No, that's all good. Thanks.
Anybody else have any questions?
I'll ask a question if no one else has one.
Yeah, go ahead.
So I'm assuming the salient feature of the Shannon entropy that you're using is that it's in some sense concave, like it's a concave moment of the flow of the dynamics. Is that assumption still true in a strictly inviscid case? Like, is it fundamentally a function of the fact that you've got a dissipative term in there that ensures that the Shannon entropy is strictly concave?
Let's go back to the definition to see if I understand exactly your question. So yeah, this is the definition of the Shannon entropy. Are you referring to, there are two definitions here. One is the Shannon entropy itself, that is always positive indeed by construction. And there is the second definition, that is this one, that has to do with how I measure causality itself. That is a difference. It's a difference between Shannon entropies. And this is also always positive, because I mean, you can just prove that mathematically. It has to do with conditional probabilities at the end. So I think it's not so much related to, so at this point where I'm presenting this, it has nothing to do indeed with fluid mechanics. So the fact that the flow is inviscid or not is not playing any role here indeed. So this may work for, if you apply the signals to the stock market, for example, and people do indeed, and try to see if they can understand what happens there, and there is no viscosity.
So if you had a strictly inviscid fluid and you sampled this Shannon entropy at 1 million different locations or whatever, you would still get a strict monotonic growth in this moment?
Yeah, I'm not sure exactly what you mean by that, but I think that as essentially it will grow as long as your signal is more, you have more uncertainty, meaning that you have more information.
Yeah.
So if the flow is more chaotic, maybe you can think of that in that way. As your flow becomes more unpredictable, then this is going to go up.
Gotcha.
If the flow is very viscous and is very predictable, it's going to go down. Maybe it's a way of framing it.
Anybody else have any questions? I don't see any hands at the moment.
Tegan has a question.
Yes, go ahead, Tegan.
So, hello, can you hear me?
We can, yes. Okay. Good to hear from you.
So thanks for the great talk. So I have two questions about the second theory part. So first one is that you examine only two modes in streamwise and spanwise directions. So did you ever look at the other modes, like not the first two, but the first 10, for instance?
Yeah, let me go to that. So I think that you are talking about are you talking about this?
Oh yeah.
First. So which are the signals that I'm using to characterize the kinetic energy of the flow? So in principle, you can keep adding more signals. That's okay. The problem is that because these are Fourier modes, and as you increase the wave number, essentially they change less and less in time. And this is because you can think of Fourier as an average. So if you have a very high wave number, what happens is that the change in time of that Fourier mode is very mild. And that's more, is not a limitation of the framework itself, it's a limitation of how to characterize the kinetic energy. So that's why I decided not to keep increasing. You can increase to the mode number 2, that should be fine, or even the 3, but if you keep going, then things don't contribute much, because if something doesn't change in time, there is no causality. For something to contribute to causality, it has to change in time somehow.
Okay.
But yeah, I mean, it's a fair question. Like, you could include more modes, then you will extend the map. It will look more complicated.
Yeah, I was just curious. And the other thing is that, as far as I understood, you computed the causality at a certain wall normal location, right?
Yeah, exactly. I can go back to, essentially I did this. I selected this band that I'm highlighting here between these red rectangles, and I use that chunk of the flow to extract the time signals there. And the reason for that is because I know that when I do that, I'm somehow isolating this energy containing eddy that is extending across this full box. I want to only isolate this largest energy eddy that fits here. And I don't want to be concerned with all the smallest ones. Usually these bands is not so sensitive. I think that in the paper there is some sensitivity analysis to these bands, how you move them. Usually that's not a big deal. So, but the main reason is to try to isolate the largest eddy containing the eddy.
Okay, I was just curious if it's possible that the some smaller eddies in the near wall or in the buffer region, do they affect those large scale eddies? Is it possible to detect such kind of mechanism?
In this case that I have, for example, you see in this plot, I will have these small eddies here. In principle, they could affect toward this large eddy that it will have in this plane. But indeed, my conclusion would be that if it's affecting them, it's more like a second order effect. Because when later I compute the causality map for this and the smallest eddies, they look very similar. And in the smallest eddies, I don't have buffer layer anymore there because they are already the buffer layer.
Yeah.
So to me, that would suggest that there is an effect, but that effect is second order.
Okay. Thanks a lot.
Looks like Vasilis has a question.
Vasilis, do you want to go ahead?
Oh yeah, thank you. Hi Adrián, nice to see you here, great talk. Going back to your aerodynamic example, to the wing example, surely that, I mean, you alluded to the fact that the line that you put there was an educated guess from studying the literature and some relationship to separation and all that. Do I understand that correctly? Or is that straight line a result of your calculations? And furthermore, if you didn't know anything about the problem, could you try some weird line painted on the wing surface, and then an iterative process in your analysis would lead to this beautiful straight parallel line?
Yeah. So to the first question, yeah, these are good questions. To the first question, I'm using a straight line. Let's see if first I understood well. So this is the actuation is going to look like this.
Yeah, who tells you that?
And so the fact that this is exactly this straight line that doesn't need to be in principle. That is just a simplification. Is the most simple function that I can choose. Is just following the leading edge somehow. And what I'm trying to get is this X location. I could repeat my analysis individually for every span-wise location, and that will give me a line that is a function of the span-wise location of the, and it will change probably. So that will happen. I'm not doing that here. It's more a simplification rather than anything else.
Okay, that's what I wanted to hear.
Yeah, exactly. And then your second question, well, in general, I will answer that if you don't know anything about a problem, you are not going to solve it. So you need to know something about the problem.
No, but you basically answered it already.
I can have many parameters for free. For example, as you mentioned, what is the particular function that I need here that could be free, the frequency that could be free, even the intensity of the jet could be free, and that will also fit within this framework. Like you could be able to do that.
Perfect. Yeah, you already answered in the first part of the question. I mean, if you can compute X as part of your analysis,
exactly.
Then eventually, with a lot of computing effort, you would converge somehow to the optimal solution.
Exactly.
Okay, thank you.
Looks like Methma has a question in the chat box. Do you want to ask your question verbally, Methma?
Oh, yes. So I have a question in the improved aircraft part, the same thing. So in this case, in the case of active flow control, we can see that the vortices which were appeared in the baseline case was disappeared. So can you explain the theory behind it or how that is possible?
Yeah, that's a good point. So essentially, this is the change you are referring to. So this was the baseline case, and you see this vortex here, and then when we apply the control, then what happens is like it disappears. So essentially, what is happening here, if we go to the base case, the reason why the flow does this and detaches is because it's losing momentum. So because there is a friction from the wind, and thus decreasing the velocity, decreasing more and more the velocity. That's why you see that the velocity here, that is measured by this bar, is going even up to zero.
Yeah.
So you have zero velocity, then you get these recirculations and the flow is detached. And that's because you can think of this as you don't have enough momentum here, because at the end the momentum is this velocity multiplied by the density.
Yeah.
So what the jet is doing, if you even think you can see the jet here somehow, what the jet is doing is adding extra momentum to the flow. So the flow was decelerating, and then suddenly I inject extra momentum, meaning that I'm accelerating the flow again. And that's what is causing this to remain attached, because by the time the flow is here, it has enough momentum to just exit and go through this, the flaps and just continue smoothly. This is an average. I have to say that instantaneously, this doesn't look so smooth, but on average, it looks like there is, and it has to do with that. There's a deficit of momentum that you compensate for when you introduce the jet.
Yeah, thank you. Makes sense now.
Thank you very much for giving a talk for our series, Adrian, and I think we should let you go get some rest.
Thank you. Thanks to all of you for joining.
And thank you everybody for joining our seminar today, and hope to see you next week.
Thank you, Adrian.
Thank you.
Thanks, Adrian.
Thank you.
Bye. Bye to all.